Okay, we are looking at introducing angle sum and angle difference identities, and that flows nicely to what's called the double angle identities, and this is for sine and for cos. It'll just be basically showing you the sum and difference identities. This video won't be proving them. That'll be for a different video. That will allow us to derive or even arguably prove the double angle identity. So in introduction, it can be shown geometrically that if we have cos of the sum of two angles, which we might call cos of a plus b, we can show this geometrically, which, as I said, is outside the scope of this video, but that would be cos a times cos b minus sine a times sine b. We've got the difference now between two angles, the cosine of the difference, and that equals cos a multiplied by cos b plus sine a multiplied by sine b. So there's the sum and the difference for cosine. Angle sum and difference identities for sine are as follows. So if we have sine of a plus b, an angle sum, we have sine of a times cos of b plus cos of a times sine of b. The fourth one out of four for these is the difference identity, and that's sine a cos b minus cos a sine b. Okay, so the double angle is when we have a situation like, here's an example, cos of 2 theta. That's a double angle, so it's got two lots of theta, so that's actually equal to the cos of theta plus theta. So there are identities for multi-angle situations. This video will basically concentrate on the double when this coefficient here is 2. So the parameter of 2 is in front of the angle, so it's two lots, meaning two identical angles added together. So looking at the double angle trig identities, assuming we proved the four identities above, which we haven't in this video, but if they were proven, we could then use that as an axiom to prove cos 2a equals cos squared a minus sine squared a. Notice that's a minus, it's not a plus, it's not the Pythagorean identity, it's a subtraction between those two terms. So we can use the first identity we had written above, so cos of a plus b. So this will be a special case of that where a equals b, so we can write a plus a. So proof, cos of a, or left hand side equals cos of a plus a, and that equals cos a. Now instead of cos b, we have a again, so cos a times cos a minus sine a, and again we have a there subbing in for that angle, which equals cos a all squared, or cos squared a, minus sine squared a. So it can also be shown, or there, I guess I should just write a conclusion here. Therefore, Oh my lord. It has been a long day. I shouldn't have RTP written there. RTP's up there and I wrote prove instead. So writing a conclusion, therefore, the left-hand side equals the right-hand side, and that means that cos a plus a, or cos 2a, equals cos squared a minus sine squared a. And that's QED, but it may, going on from that, bit of a corollary here, it can follow. It follows that, some people call that a corollary. There's two other forms of the double angle for cosine that I'd like you to know. If we have cos 2a equals cos squared a minus sine squared a, we can come to the next commonly used identity. If we use NB, the Pythagorean identity, which we've seen previously, cos squared a plus sine squared a equals 1. We can make a replacement here. We've got cos squared a minus, now we can rewrite sine squared a over here in the Pythagorean identity. We have 1 minus cos squared a. So wherever we write sine squared a, we can write 1 minus cos squared a, like here. Just like here. We can simplify that, and that would be cos squared a. Alright, now we've got minusing and negative essentially, so we have another plus cos squared a, and the minus is in front of the 1. So that would be 2 cos squared a minus 1. So I'd like you to know that result, 2 cos squared a minus 1, and of course that result. And there's a third one coming up. Alright, so going back to cos 2a is cos squared a takes sine squared a again. We can go back to the Pythagorean identity and rewrite it in terms of cos squared a as the subject. That would be 1 minus sine squared a. So wherever we see cos squared a, we can write 1 minus sine squared a, like I've just done. And we still have the minus sine squared a there. We got 1 minus 2 lots of sine squared a. And that's the other result there. Okay, so third result. So there are 3 results there for the double angle cosine identity. Okay, now to generate we're going to in a minute generate the sine 2a identity. And just like we did with cosine, with the sine, we're going to use the sine sum of 2 angles. So that sine from earlier in the video, sine a times cos of b plus cos of a times sine of b. So sine 2a equals sine of a plus a, where we substitute for b, we substitute a in there. Alright, so we're just going back to that first line, and that'll be sine a cos a minus, plus cos a sine a and those two things are like terms. So Alright, we have two of the same thing. Thinking of commutativity, alright, so we have two lots there of Sine A, Cos A. Alright, you can see them there. There's one, and there's the other one. They're exactly the same, those two terms underlined with green. So that's our result there for sine of 2A is 2 sine A cos A. We notice this is what's called the QCAA formula sheet for specialist maths. This may or may not be relevant to you watching the video. If it is, you'll notice that in the trigonometry section we've got things from the last three videos here. Pythagorean identity in its three forms. We've got angle sum and angle difference, formulas for sine and cos, all those identities there. We have the double angle identities that we've just looked at there. So far, recently we've covered those first three. The product identities come later on in the course. So it's about knowing when to use them, but if you had to do a proof, you do need to know your skills, okay? So those are given as formulas, however, it doesn't diminish the importance of underlying skills.